This giant machine has been designed to heat and hold a very high temperature gas in imitation of the sun's processes. Many believe it is the most ambitious experiment ever attempted by man. For the future, we need guaranteed very long-term sources of power. That is why we must try for fusion. In a fusion reaction, energy is released when light atoms are fused together. This energy or heat can also be used to generate electricity, as in a fission power station. The great lure of power from fusion is that the basic fuel is deuterium, a form of hydrogen. It can easily be extracted from water, oceans, lakes or rivers. It's inexhaustible. Every atom is an organized structure like a mini solar system. This is the smallest atom, hydrogen. Its nucleus is a particle called a proton, which carries a positive electrical charge. It has one electron, negatively charged, which circles round the nucleus. This is an atom of deuterium, an isotope of hydrogen. Its nucleus has two particles, a proton and a neutron, which has no electrical charge. Deuterium occurs naturally in water. Tritium, another isotope of hydrogen with a nucleus of two neutrons and a proton, does not occur naturally and has to be manufactured. The likeliest way to fusion power uses the nuclei of these two atoms. But each nucleus has a positive nuclear charge. So when they come close together, the laws of nature mean they repel one another. The only way to force them together is to make them collide at thousands of kilometers per second. To do this, they are heated to enormous temperatures, around 100 million degrees centigrade, 6 or 7 times hotter than the center of the sun. At that temperature, the particles are stripped of their electrons, which race around independently. This gas mixture is called a plasma, in which some of the nuclei will collide and fuse together, forming a new single nucleus and ejecting a neutron. But how can this superhot plasma be held together so that collisions can happen? If the plasma hits the walls of a container, it cools instantly. This loss of energy prevents fusion reactions happening. Magnetism can be used to hold the plasma because charged particles can be trapped in a magnetic field. The particles travel around the lines of magnetic force so that they are prevented from moving rapidly towards the walls. To stop the plasma escaping from the ends of the container, it is bent back on itself like a tire and called a torus. The plasma is trapped in a ring with no ends through which to escape. The magnetic field is set up by placing a series of magnetic coils around the torus. This invisible hand grips and shapes the plasma into the best possible form. This basic shape has been the most successful in experiments so far. It has been chosen for JET, the Joint European Torus. Most of the energy produced from fusion reactions will be released from high-speed neutrons flying out of the plasma. In a commercial fusion reactor, the plasma will be wrapped in a blanket containing lithium, which absorbs the neutrons. These neutrons, traveling at thousands of kilometers a second, heat the blanket as they are slowed down by colliding with the lithium. It is this heat that will be used to generate electricity. For 20 years, here at the Culham Laboratory, the UK Atomic Energy Authority's Centre for Fusion Research, scientists have been working towards the goal of power from fusion. Since 1973, work at Culham has been part of a coordinated West European fusion program. And since 1978, another team of scientists and engineers from many European nations, the member states of the EEC, plus Sweden and Switzerland, have been working on a project called the Joint European Torus, JET for short. JET is a great step forward along a road which will be difficult and long. But scientists and engineers in laboratories throughout the world are showing how to make common cause in a project for the ultimate good of people everywhere, creating energy for the 21st century.